Alright, welcome back for 8.3. In 8.3, what we're going to do is we're going to look at the ionization of water. And the ionization of water is very important because we're going to be getting closer and closer to understanding how pH works. And pH is the measurement of how acidic or how basic something is. So in water, we've already kind of seen this, that we can transfer a proton to from one water molecule to the other, okay? And so when we do that, we get the hydronium ion and the hydroxide ion, okay? And so and they've just kind of drawn them out so with the Lewis structure so you can kind of see what that looks like here. So it's interesting because in just how water reacts, one water is a base and one is an acid because one accepts and one donates. So we've already said that they could act as either one, but when they interact with each other, that's exactly what they do. In pure water, the ionization of the water molecules produces equal amounts of hydronium ion and hydroxide ion. The molar concentrations are in brackets. So when you see this right here, that means the molar concentration of the hydronium ion or the molar concentration of the hydroxide ion is equal to whatever. In pure water, they dissociate so that you have 1 times 10 to the minus 7 molar hydronium and 1 times 10 to the minus 7 molar hydroxide. If you add acid to pure water, you're going to increase the hydronium. This causes the hydronium concentration to go above 10 to the minus 7. Okay, now remember how this works. When you're in negative exponents, if I'm going to be a stronger concentration than 10 to the minus 7, it'll be 10 to the minus 6. Because 10 to the minus 8 is a smaller number than 10 to the minus 7. As I increase the hydronium ion concentration, I am going to be decreasing the hydroxide. When I add a base to pure water, I'm going to increase the hydronium ion concentration, and that causes it to be higher than 10 to the minus 7, and it's also going to cause a decrease in the hydronium ion concentration. So in an acidic solution, you're going to have a higher hydronium concentration than hydroxide. In a neutral, they're going to be equal. They're both going to be what? 10 to the minus 7, so that's our neutral point. In a base, you're going to have a higher hydroxide than you are hydronium. So where this 1 times 10 to the minus 7 comes from is a calculation that our buddies the mathematicians did for us called the ion product constant, or Kw, for water. And this is the product, so that's multiply, of the concentrations of hydronium and hydroxide ions, so you multiply them together. So the Kw equals the hydronium ion concentration times the hydroxide concentration. So if we've already told you that they're both equal, right, and they're both 1 times 10 to the minus 7, so 1 times 10 to the minus 7 molar for the hydronium times 1 times 10 to the minus 7 molar for hydroxide gives you 1 times 10 to the minus 4. Because when you multiply exponents, hopefully you remember this from a math class, you add them together. So 10 to the minus 7 times 10 to the minus 7 equals 7 plus 7, 10 to the minus 14. In neutral, acidic, or basic solutions, the Kw is always 1 times 10 to the minus 14. Okay, that is, we said Kw was a constant. So constantly you're going to have to equal 1 times 10 to the minus 14. So if it's neutral, you're going to be equal. You're going to have 10 to the minus 7 and 10 to the minus 7. They equal minus 14. If your hydronium ion concentration is 10 to the minus 2, which is very much higher than 10 to the minus 7, okay, then in order for it to still be equal to the 14, the hydroxide concentration has to change to 12. See how that works? So 7 plus 7 is 14. If the hydronium is 2, this one has to be, the hydroxide has to be 12 because they still have to equal 14. So 2.5 times 10 to the minus 5. Now when you start changing this number from a 1, you've got to then do some calculations on your calculator, but they still have to equal exactly 1 times 10 to the minus 14. Notice when I have a larger number in the exponent here, that's telling you that it's a base. So if this number is larger than 7, it's a base. If it's less than 7, it is an acid. And whatever this one changes to, the other must change to equal the 14, the minus 14. Clear as mud? Okay, so if you're going to calculate the hydronium and the hydroxide ion concentrations in an aqueous solution, that is in water, first you're going to write the kW for water, and we already know what that is. It is simply 1 times 10 to the minus 14. Okay? Solve the kW for the unknown. So you're going to have to be given one of these. Okay? And so you're going to solve for the other one. Then you're going to substitute in the known and calculate this, the one you don't know. So if you know the hydronium, then you put that in, you substitute, and you're going to be able to calculate this. And I'm going to show you how to do that. So what is the hydronium ion concentration if the hydroxide ion concentration is 5 times 10 to the minus 8? So kW equals H3O plus times OH minus, and that's always going to equal what? 1 times 10 to the minus 14. So if I'm solving for one of those, what I have to do is I have to divide both sides. Let's see, OH. I have to divide both sides by OH minus. That's where this is coming from. Okay, and so these will cancel out because I have one on top and one on bottom. So that gives me H3O plus equals 1 times 10 to the minus 14 divided by the OH. So I substitute the 5 times 10 to the minus 8 and put it in here, and I solve for it. And the answer I'm getting here is 2 times 10 to the minus 7. Put this in your calculator to make sure that you can get this. You need to put each of these in parentheses, okay? So you need to do parentheses 1 times 10 to the minus 14 divided by parentheses 5 times 10 to the minus 8, and then enter, and you should get this number. So see, if you've got a different calculator from the TIs that I'm used to, you need to go ahead and practice with your calculator to make sure that you can get the right answer. So here's one for you to try. Lemon juice has a hydronium ion concentration of 2 times 10 to the minus 3 molar. What is the hydroxide concentration? And remember, all you're going to do is you're going to divide 1 times 10 to the minus 14 by the concentration that you're given to give the other one. Put me on pause and try it. Okay, so first you know that it's 1 times 10 to the minus 14. You know, they're taking you step by step through it, so you can do these slowly and make sure that you know the steps. And so when you divide the 1 times 10 to the minus 14 divided by 2 times 10 to the minus 3, you should get this answer. Make sure you're getting the right answer. Make sure you're putting it in your calculator correctly. Here's another one for you to try. The hydroxide ion concentration of an ammonia solution is 4 times 10 to the minus 2 molar. What is the hydronium ion concentration? And it's the same exact way, right? 1 times 10 to the minus 14 divided by the hydroxide ion concentration will give you the hydronium. And you should get 2.5 times 10 to the minus 13. Alright, so that's the end of 8.3. So that's all about ionization of water, and the next section that you're going to see is how we use that to figure out the pH. So if you need to practice some with these calculations, make sure you get proficient at that before you go on to 8.4.